Welcome to Lesson 8. So we're just starting our notes in week 2. So last week we looked at discrete random variables and their probability models. This week we're going to look at continuous random variables. So just kind of to reiterate what we were talking about, random variables, it is a quantity that for every event in a sample space has a probability. If we are dealing with discrete, as we were last week, usually our discrete random variables are described as counts, often as like 0, 1, 2, and possibly up through a maximum value, possibly on forever, depends on how it's defined, but typically these are non-negative integers. This week we're looking at continuous random variables, so that means, for some interval of values that x is defined on, x can take any value. So maybe I'm looking at weights. I'm going to look at cat weights because I know about what they weigh. And it could be anywhere from like 5 pounds to 25 pounds. And it could be, 13 pounds. It could be 13.21. It doesn't have to be an integer value. That's the key thing for continuous. It could be anything in the interval. So here for continuous probability models, we, rather than calling them PMF, we call them probability density functions, or PDFs. Quite honestly, a lot of people will call the PMFs PDFs. PDFs are a really, really common language to use for both. Just know probability mass function is for discrete. Probability density function is designed to be for continuous. We tend to use them fairly interchangeably though. So similar to before, the values in the PDF cannot be negative because they're probabilities. So they're greater than or equal to 0. And now instead of using a summation, because we don't have discrete counts, we are now going to, the probability of our sample space, you could say negative infinity to positive infinity. It could be narrower bounds depending on where x is defined. But if you take that integral of the PDF over the entire defined sample space, the area should equal 1. And then, if I wanted to know, if I want to know the probability that x is between a and b, absolutely, you can go ahead and just integrate from a to b. And one important distinction, something that makes it a little bit different from discrete, is the probability that x is equal to a specific number, so that x is exactly equal to a value, is 0. Because if you were to integrate from a to a, there's no width to that interval, so the area would be 0. But what that means is, in the continuous case, the probability that x is less than or equal to a is equal to the probability that x is less than a. This is not true if you're in the discrete case. So be careful. In the continuous case, you can say this is true. This will not be true for discrete. So here's an example we're going to look through. Is looking at propane. So we're going to say, okay, well, x is a continuous random variable, and x is the weekly demand for propane gas. So my random variable, just x, is weekly demand for propane. And just looking here, it looks like it was in thousands of gallons. So data are recorded over time, and we have this following model here. So we have that our PDF is equal to 2 times this quantity when x is between between 1 and 2. And then this is important too, it's 0 everywhere else. So this is saying, hey, there's no probability whenever we're outside of that interval from 1 to 2. So we want to know, does the area under f of x equal 1? So we would say, okay, well, from negative infinity to positive infinity, 2 times 1 minus 1 over x squared dx What's interesting here is it's not, if you look at these bounds, you don't have to go from negative infinity to positive infinity to observe everything. I can go ahead and say, oh, from just 1 to 2, because that is where x is defined. So just redefine it here. I'm going to take the 2 out. It makes it a little bit easier on me. But you don't have to. You can distribute it if you like. So 1 minus 1 over x squared dx. So I'm going to end up getting 2 times x plus 1 over x evaluated from 2 to 1. So that's going to be 2 times 2 plus 1/2 minus 1 plus 1 over 1 is just 1. This ends up being 2.5. This ends up being 2. So you end up getting 2 times 1/2, which is equal to 1. So for some reason, if we ever give you a function like this, and we say, hey, is the area for the sample space is equal to 1, and it is, this is good. If it's anything besides 1, that means that this is not a legitimate PDF. It won't be a PDF if it doesn't integrate to 1. So be cautious. And I know that we will intentionally ask that kind of question. Hey, is this a legitimate PDF? So then a follow-up question would be to find the probability the demand will be less than 1.5 thousandths of gallons. So like 1,500 gallons, basically. So what it's asking for is, so our lower bound is 1, and our upper bound, we want to go up to 1.5. 2 times 1 minus x squared dx. So I'm going to get really similar steps here. It's going to be x plus 1 over x. But now it's going to be evaluated from 1 to 1.5. So no, this is no longer 2, because I only want to know the probability that it'll be less than. So specifically, this is equal to the probability that x is between 1 and 1.5. That is what we're looking for. So resuming here, this will be 2 times 1.5. Tell you what, I'm going to switch to 3/2. It's easier for me to see. 3/2 plus 1 over 3/2 minus 1 plus 1. So I'm going to get 2 times 3/2 minus 2/3, just using fraction rules here, minus 2. I might run out of a little bit of space here. It ends up coming down to, I multiply by 6 over 6, just because I wanted to go ahead and get rid of all the fractions here. So I end up having 1/3 times 9 plus 4 minus 12. So it's going to be 13 minus 12 is 1. So 1/3. So what we're ultimately looking at here is 1.5 is right around here, and we're finding this area under this curve. That's what we're looking at. So the probability the demand will be between 1 and 1.5 thousandths gallons, that happens about 1/3 of the time. So that's what we're looking at here. So now that we've described our PDF, we're also going to describe our CDF, so a cumulative distribution function. It's going to be very similar to what we did in the discrete case, except now we're using an integral instead of a summation. So whatever the lower bound is of x, so wherever x is defined, that sample space, and then the upper bound will be x. So it's just the probability that x is less than or equal to some value. So we would plug in a value here. So things to know, the CDF is always going to be between 0 and 1. In fact, it's a non-decreasing function, so it starts at 0 and gets closer and closer to 1. And once you've observed the entire sample space, the area will be 1. So if I want to know the CDF of a value a, I'm just asking what is the probability that x is less than or equal to a. So I would evaluate that at the integral from the lower bound of x to the value a. If I want the value above a, so I want the probability that x is higher than some value a, then I'm just going to take 1 minus f of a. And if I want to have the area between 2 points, so if I have, I'm going to describe this as a, we get that one there, and b. If I want to go ahead and I want to say I want this area here between a and b, I'm going to start off with the area from the lower bound to b, and then I'm going to subtract the area below a, and that'll give me just the area I want. So I'd take CDF of b minus CDF of a. You'll know if you subtract in the wrong order because you'll get a negative value. If you subtract in the correct order, you should not get a negative value. So if you were to do this math and you get a negative value, that's an indication, oops, I switched my bounds. I need to go the other way. So back to our propane example. So x is a continuous random variable. We are assuming that x is the weekly demand for propane, probably in a specific region in a specific time period, but we don't need to get that specific for this example. And they might say, okay, well, find the CDF function of x. So what that's saying is we want to be able to find a general form for the CDF. And no, not every single continuous random variable is going to have some nice general form, but some will. So f of x here, it would be my lower bound, so 1 is the lowest that x will go to, all the way up to whatever x is, 2 times 1 minus 1 over x squared dx. So this is still, we're going to have something very similar to what we did before. So it's x minus plus 1 over x. But this time, so the lower bound is the same, it's still 1. But note that the upper bound now is x. Anytime we ask for the CDF, the upper bound should be x. So if I want to do this, it's just going to be 2 times x plus 1 over x minus 1 plus 1 over 1. So minus 2 here. So here, I'm going to get 2 times x plus 1 over x minus 2. You can go ahead, you can distribute. It's not going to make a big difference here. So yeah, I'll have that. So for me, I like to put it as piecewise. So f of x, capital F. Note, when we are defining these, the PDF has a lowercase f. The CDF gets an uppercase F. We are very, that's an important distinction. So capital F of x. It's going to be 0 from x less than or equal to 1. That's because we don't have any area up to that point. And it's going to be that 2x plus 2 over x minus 4. I'll tell you why I'm going to move this. When x is between 1 and 2. And then once I get to that boundary, once I get to 2, x greater than or equal to 2, then the value is just going to be 1. So it's something that it's non-decreasing. Usually we like to say increasing, but it doesn't always have to be strictly increasing. And then it gets to 1, and then it levels off. Because at that point, you've observed all of the sample space. So you've observed 100% of all of the possibilities. So that's why it's equal to 1. So then we have some more questions we can ask. So using our CDF, so remember it's going to be 2x plus 2 over x minus 4 when, not 0, when x is between 1 and 2, and then 1 if x is higher, equal to or higher than 2. So I can go ahead and use this. So using the CDF, find the probability that the demand is going to be less than 1.5 thousandths gallons. So we calculated this probability before on an earlier slide. So we're asking 1.5. This. So we can go ahead and say, okay, well, probability that this is less than 1.5, that's just the CDF 1.5. So I'm just going to plug that in. So 2 times 1.5 plus 2 over 1.5 minus 4. And when I do this here, I'm just going to get 3 plus 4/3 minus 4. So 4/3 minus 1, it's going to just be 1/3. Which this probability should match what we got earlier. But now we used CDF specifically to get it for us. So now if I want to go ahead and find the area between 1.5 and 1.8, we are going to go ahead and use that former part, but just setting it up, probability x is between 1.5 and 1.8. I can set that up as the CDF 1.8 minus the CDF of 1.5. So I can go ahead, set that up. It's going to be 2 times 1.8 plus 2 over 1.8 is 9/5. And I just do that because it's easier for me to look at fractions that way. Minus 4 minus, recall this part was 1/3, minus 1/3. So I end up getting what? 3.6 plus 10/9 minus 4 minus 1/3. I'm just honestly trying to keep thirds together, keep tenths together, something like negative 0.4 plus 7/9, because 1/3 will be 3/9, so negative 3/9 there. So if I go ahead, rearrange it, 7/9 minus 4/10, multiply top and bottom by 90ths, just getting rid of the fractions, end up getting something like 70 minus 36 over 90 is 34 over 90. That would be our exact answer. You can go ahead and put into decimals. That's about 0.3778. So if I want to know the probability that the demand is going to be between 1.5 and 1.8 thousands of gallons in a given week at this facility, that happens about 37.8% of the time.